The goal of this section would be to prove that if we're able to multiply matrices with some exponent in the asymptotic complexity, then we're able to get inverse of a given invertible square matrix with the same asymptotic time complexity. The first lemma that we'll need is about multiplication of non-square matrices. So suppose that we have two matrices of order m by m and of order m by n, where n is larger than m. Then the result of this multiplication, an m by m matrix, and we can actually split this matrix into blocks of size m by m and see that each such block is the result of product of our square matrix by a corresponding block of our rectangular matrix. So thus, to perform the multiplication, we need essentially n over m multiplications of square matrices, which can be done with complexity big O of m to the power of matrix multiplication exponent plus little o of 1. So in the end, our time complexity for multiplying such two matrices would be big O of n times m to the power of omega minus 1 plus little o of 1. So this would be our first node. The next result that we'll need is on inversion of a lower triangular matrix. So suppose that we have an invertible n by n lower triangular matrix A, and let's write it in a block form so that we have four blocks of order n over 2, which will denote by B, C, D, and here we have an all-zero block if A is a lower triangular. B and D are also invertible lower triangular matrices if A is an invertible lower triangular. So it turns out that A inverse can be written in the following form. As well, in a block form like this, blocks are B inverse minus D inverse C, B inverse, D inverse, and an all-zero block. So we can verify that indeed the product of these two matrices gives us an identity matrix. And what do we need to compute A inverse in this form? So let's assume that T of n is the time needed to compute an inverse of a lower triangular matrix. Then for this computation, we need to multiply matrices, which can be done in time big O of n to the power of omega plus little o of 1. And also we need to compute two inverses of lower triangular matrices, B and D. That's 2 times T of n over 2. And this is our upper bound for T of n. The master theorem tells us that this is dominated by this term, and eventually T of n is big O of n to the power of omega plus little o of 1. So it turns out that inversion of lower triangular invertible matrices can be carried out in time the same as the multiplication of the matrices. Clearly, for upper triangular invertible matrices, the result would be exactly the same. And now we'll move on to proving that for arbitrary invertible matrices, we have still the same time complexity. To prove this, we'll need an algorithm for LUP decomposition. The LUP decomposition of a matrix is a decomposition into products of three special kinds of matrices. Assume that A is a matrix of size m by n, where m is less or equal to n, and rank of A is equal to m. Then LUP decomposition, or lower triangular, upper triangular, and permutation decomposition of A, is a product of three matrices L, U, and P, where L is a matrix of order m by m, which is lower triangular, so we have zeros above the main diagonal. U is the m by n matrix, which is upper triangular, so if we bring the main diagonal here, we'll have zeros under it. And P is an n by n permutation matrix. And the permutation matrix is a 0-1 matrix where ones stand on some transversal of the matrix. Such matrix defines a permutation of the columns of the matrix to which it is being multiplied from the right And if we multiply a matrix by a permutation matrix on the left, then we permute the rows of the matrix. So we have these decomposition available for any matrix with these properties, as it turns out, and also the time needed for this decomposition is big O of n to the power of omega plus little o of 1, which we'll prove in a few moments. And before we proceed with the proof that such decomposition can be done efficiently, let's now first discuss what it implies. And our ability to build such decomposition quickly implies that we're able to invert arbitrary invertible matrices quickly, not just upper or lower triangular, because if every matrix can be decomposed into L, U, and P, then it means that a square matrix can be decomposed into a lower triangular square matrix, upper triangular square matrix, and a permutation matrix. So if A is an invertible square matrix, then L and U will be lower and upper triangular matrices, and they will have inverses. And permutation matrix always has an inverse, which is computed combinatorially, not algebraically. So we just need to take an inverse permutation and take the matrix of it. So if A turns out to be, say, an n by n matrix, then we can first decompose A into L, U, and P, and then we know that A inverse would be the product of inverse matrices for these, but just in different order. It would be the product of P inverse, which is computed combinatorially quite quickly, U inverse, which we can compute efficiently as it is an upper triangular matrix, and L inverse, which is a lower triangular invertible matrix, and we know also how to compute these guys efficiently. And now we have the product of three matrices, which can be done again with complexity defined by a matrix multiplication exponent. Also, we note that as soon as we are able to decompose matrices into L, U, and P, we are able to compute determinants efficiently. Because the determinant of a lower triangular matrix is the product of elements on its diagonal, the determinant of upper triangular square matrix is the product of its diagonal elements as well, and the determinant of a permutation matrix is plus or minus 1, which we can also infer combinatorially. So both computing inverses and determinants is actually doable efficiently. And next we'll learn about how to do LUP decomposition.